Alright, ladies and gentlemen, today's class recording has started. So I watched some YouTube videos with my son over break, and so I feel I should start all of my videos now with, hey, if you like today's content, subscribe to my channel. Really helps the channel out a lot. Alright. So I should, every day I think I'm going to start that. So if you like today's content,
Go ahead and subscribe.
go ahead and subscribe.
Smash
Text
that
a
like.
like or voice a comment. It helps out the channel a lot. So. All right, Frank, were you willing to help me out here this morning? So, all right. So Frank's going to stand over there and he's going to grab this long spring here. Okay. And that's good. That's good. Frank. Good. Yeah, you good. All right. So in the last two chapters, especially, last two units especially, we talked a lot about energy. So what's our working definition of energy that we've used like the whole time? The ability to do stuff. The ability to make things different than they were before. The ability to change things, okay? So we talked about that in forms of mechanical energy with like kinetic and gravitational potential and elastic potential, right? And then the last unit we talked about thermal energy, right? The motion of microscopic particles, make things different there and stuff like that, okay? So I'm going to take this spring here, and I'm going to make Frank's hand move, even though I'm not there, right? Here we go. All right, so there we go. Frank's hand moves, okay? But I wasn't there to make Frank's hand move, but I still made it move, right? Last unit, we talked about what type of energy transfer was going on. So what would be the type of energy transfer that we're talking about in this situation of me making Frank's hand move from across the room? Okay. We talked about three types: conduction, convection, and radiation, right? First, is this radiation? No, right? There's matter between me and Frank's hands. So that means two choices: conduction and convection, right? But if we take a look, right? I was going to do this before class. Hey, Frank, see that drawer that says tape right there? Nope, next one down. Yeah. Grab me one of those rolls of masking tape. Okay. So we go here, and I'm going to take this roll of tape, and I'm going to do maybe here. This tape is not actually vacation, we were talking about this morning that you guys all hate like the first day back from break, and stuff like that, But quite honestly, from a teaching standpoint, today isn't the worst day. Tomorrow is the worst day. Because even though you say you hate it, like you're back and you're like, oh, like it's the first day back and you're kind of jazzed to be back and stuff like that. But tomorrow is literally like zombies walking through the hallway. Like so I agree. All right, so I'm going to take this tape. Put it around the spring just like that. Okay. And I'm going to stretch it out here. Okay. And the tape is now right in front of Joe's face, right? Okay. And so I'm going to make a disturbance in this string again, right? And Frank's hand's going to move, right? It's going to come back, so like that, okay? But where does the tape end up?
In front of Joe's face.
Right in front of Joe's face. So is this conduction or is this convection?
Conduction.
Conduction. This is conduction, right? Okay. Because even though we saw the spring move and we saw the disturbance move through the spring, did anything actually go anywhere? Right? The spring's in exactly the same place that it was. All right. So I think that we probably know by now. Okay. We call this disturbance that I make in this spring a wave. Right. So I create this here. Right. Frank's hand moves on the other end, it comes back to me, right? My hand moves, but it comes back to me, and we go back and forth, and eventually the spring settles down back to what it really was, right? So, what is a wave? Frank, you get like a wave. Just drop it, Frank. All right. So, yep.
What's this?
This demonstration right here. This is basically about it.
For that?
Yeah, basically this is me. All right. So. Let's get into all right, so let's get into answering this first question. What is a wave? Based on our demonstration right here, do you have an answer for what a wave is? Well, what did the wave do? It wasn't a very productive wave, but what did that wave do? It transferred what? Energy, right? It made Frank's hand move on the other side, right? So, what are waves? Waves are a motion of a disturbance, not the motion of matter, right? Back when we looked at the location of that piece of tape before and after the wave went by is exactly the same spot. Okay? But more importantly than it's a motion of a disturbance, right? Waves carry energy from one point to another, but no matter is moved. And that means, at least in this case right here, right, from what we just saw, that's an example of what type of energy transfer? Conduction, right? Where we're passing that energy along from one to the next, to the next, to the next. Okay? All right. What has to happen in order for a wave to occur? A disturbance, right? Okay? Or some kind of sorry, apparently I forgot. Yeah, I forgot that line right there. I apologize. I basically have done that for, every year for the past 2 years, and I keep forgetting to change it. So we need a disturbance. Okay. That disturbance does what? Work. Frank, did you read this chapter beforehand? Right? Wow.
Probably should.
Okay. So, that disturbance causes work to be done. Because, Frank, we go back to our definitions from a couple chapters ago. What is work? A transfer of energy, right? So my hand does work on the spring. And then that transfer of energy to the spring is carried from one place to the next to the next. So, letter C, number 1, work needs to be done. A wave carries, right? So, the wave transfers the energy of the disturbance from the source, right, to some other place. So the energy is transferred, but no matter moves anywhere. Okay? Good there? All right. So let's flip it. We'll come back to these pictures here in just a second. Let's flip it over to the back side. Okay? And we are going to use for our discussion for most of the next couple weeks, or most of the next week or so, we're going to talk about specifically mechanical waves. All right? So, what has to be there to allow me to move Frank's hand on the other side of the room? Well, in this case, it was the spring, right? So there has to be something that transfers or carries that disturbance from one side to the other, all right? So, mechanical waves need a medium to travel through. The medium is the matter that carries the energy from one place to the next. Say again? Right, so the material, right, is a generic term of matter, yes? Right. Yep. There has to be something that carries that disturbance from one place to the other, all right? Okay? That material that carries the wave is called the medium. And, right, mechanical wave is created when an energy source causes a disturbance, and the energy of that disturbance is carried through the medium. Energy source causing a disturbance, right, is just a long-winded definition of what? Work, right? We need work in order to make a wave. Energy source causing a disturbance, transferring that energy. That's the work that's being done. That work is required for a wave to be created. Okay? Good there? All right. All right, let's talk about a couple of different types of mechanical waves. Let's talk first about transverse waves. All right? By definition, a transverse wave is a wave that causes the medium to vibrate at right angles to the motion of the wave. So if you go down a little bit farther on the page, Roman numeral number 3, types of mechanical waves, letter A is transverse. Going back to our definition at the beginning of class, or going back to our demonstration at the beginning of class, right? We have a spring that's stretched out between me and Frank. Which way did I move my hand to start the wave? Up and then
Down.
back down, right? So I'm moving my hand up and down. The spring moves up and down, but which way is the disturbance or the energy moving? Horizontally, right? The energy went from my hand, which was way over on this side of the room, to Frank's hand, which is way on the other side of the room. The spring is going up and down, but the wave is moving side to side. Up and down, side to side, right? What angle is that?
Right.
That's a right angle, right? 90 degrees, okay? So, a transverse wave is what you guys probably think of when you think of a wave, all right? So this girl in the picture is doing something real similar to what I was doing in the demonstration. So transverse waves can go up or down, but they can also go side to side, right? If the spring is moving side to side, but the wave is moving front to back, that's a right angle as well, okay? So both of those are transverse waves. When we look at transverse waves, there's a couple of parts that we identify. So first, we talk about the crest. The crest is the highest point of a wave from its resting position. So in this picture here, those two things would be crests. You might want to make a note of that there on the picture, okay? And then the opposite side we call a trough, right? Those are our lowest points. Those are going to be down there. Okay? So crests and troughs represent how far that wave moves from its resting position. Okay. All right, good there? All right. Frank, want to do another demonstration for me? Grab this scenario here. He's on the end. All right. So, you guys, we just talked about transverse waves, right? That's a transverse wave, right? Chris, you see that tape that's on Slinky right in front of you right there? All right.
Right in front. Why are you looking at the ground? You said right in front of you. Oh, that one?
Yeah, that was that tape. It's right in front of you right there.
Oh, I see. Oh my God.
There we go. All right, so here's what I'm going to do, right, Frank? You just have to hold on, okay? So instead of creating just one wave, I'm going to create several waves, right? I'm going to do something like this. All right. So Chris, can you see that tape?
Yeah.
Which way is it moving?
No, you can see that. Up and down.
Up and down, up and down, up and down, up and down, right? But is it actually going anywhere? Not really, right? It always ends up right back where it started each time, okay? Another example that Matt, and it's very frankly,
Triangle. It's
sorry,
kind of
we'll
moving.
do that. All right, and then if we do it this way, okay? Okay. Now which way is it moving?
This way.
Right?
Side to side.
Right, side to side, as this wave is moving front back.
It's
right?
moving.
And I know we got a little twist going on here, right? Now it's actually moving up and down and front to back. So that's a three-dimensional wave. Right? know, I took this one and I moved it this way, right? Scrunched it up here and then let it go.
Whoa.
Sick.
Oh, it is pretty sick. Alright, so now, right, Chris, if we take a look at that tape, right? Okay. Which way is it moving now?
Left and right.
It moves like left and right. But that's also the same direction that the wave is moving as well, right?
Yeah.
So I should say correct. The wave is moving from me to Frank, and that tape is moving in the same direction, right? Another type of wave that we refer to.
Oh, right.
No, it's not Frank's fault. All right, the second type of mechanical wave we talk about is a longitudinal or a compression wave. And so, in this case, we have the medium vibrating parallel to the direction of the wave movement, right? So when Chris is looking at that piece of tape, right? It was moving up and down at first. It was moving front to back second. Those are both perpendicular to the wave movement. But that last example, it was moving in the same direction as the wave movement. And so we end up with the spring looking something like this, where we have certain areas of the spring where all the coils are crunched together, and then certain areas of the spring where they were all spread out. We call those areas where the spring is scrunched together compressions. And then the area where the spring is stretched out, we refer to as rarefactions. But more importantly, we have that spring sort of compressing, stretching out, compressed, stretched out, compressed, stretched out, but that's the same direction that the wave is moving. Okay? So, to wrap this up here, let's flip it over back to the front side. Okay? And we have two examples of mechanical waves. Now you should know that the one on the left, the one with the string, is what type of mechanical wave? A transverse mechanical wave, okay? Then the one on the right, we now know we call what kind of a wave? A longitudinal wave. But more importantly, just like we saw with our little pieces of tape, right? They use a little piece of ribbon here, okay? And Chris, you kind of like verified for us, right? That tape moves, a little piece of tape moves, but does it actually go anywhere? No, it ends up right back where it started, right? It vibrates sort of from where it started, but it never actually goes anywhere, right? So it says, how does the motion of the ribbon illustrate the point of the wave, the motion of a disturbance, not the motion of matter? After the wave passes through the medium, where does the piece of tape or the ribbon in the picture end up? Right back where it started, right? So no matter is actually moving. It's displaced for a little bit, but it always ends up right back where it started. Okay? Good there? All right. Tomorrow, we will talk about describing waves and how waves differ from other types of waves, and get into some more definitions at that point. Okay? Thanks, everybody. Don't forget to press the like button. If you have a specific question, leave it in the comments below. Maybe I'll get it in a future video.